Hello, this lecture covers ocean circulation. So we are basically continuing on from ocean-atmosphere interactions, and we're going to be talking about ocean currents and how the temperature of different currents and how wind direction controls the distribution of these currents. So for the first slide here, I have the distribution of Earth's sea surface temperature. So red being the warmest regions and blue and green being the coldest regions. So we can see here along the equator we have the warmest water, and at the poles we have the coldest. And last week in our lecture on ocean atmosphere interactions, we discussed why Earth is hottest at the equator and coldest at the poles. And that has to do with the amount and concentration of solar radiation. So we're gonna keep using those same principles that you learned last week today. So ocean currents are basically columns of moving seawater. And that movement can be either horizontal or vertical. So surface ocean currents involve horizontal motion. Deep ocean currents involve vertical motion. So surface ocean currents are at the surface, right? They're in contact with our atmosphere. And because of that, they're going to flow in a similar pattern to the major wind belts. And these are the ocean currents that also have very significant effect on coastal climates. They're also the main conveyors for transferring heat from warmer to cooler regions. Deep ocean currents involve vertical motion, and because of that, it provides oxygen to the deep sea. So it's a very important, although slow moving ocean current that can deeply affect marine life. So this slide here demonstrates the difference in the motion between the two. Surface currents are primarily horizontal motion, and they're driven by the wind or major wind belts. Deep ocean currents are vertical and sometimes horizontal motions that are mainly driven by differences in density. Density can be a factor of the temperature, so colder water is more dense, and also the salinity, right? So how much salt is present in the seawater. This lecture here mainly covers surface currents. So in our next lecture, we'll be covering a phenomenon known as El Nino, and we'll also be talking about deep ocean currents. So today we're mainly going to concentrate on surface currents because they are the most complex. And this next exam that's coming up is the hard one. So make sure you spend good time with this material. And if you're still struggling, give me a ring during office hours. If you're having any trouble with the quiz or anything like that. So surface currents are what is in direct contact with the atmosphere and wind belts. And they're a result of the frictional drag between the wind and the ocean. So driven by Earth's major air currents, they're going to move in a similar direction. But they're not going to move exactly parallel to the wind direction. So we'll come back to this in a few slides. But this is due to the Coriolis Effect, right? That deflection of moving objects to the right or left on this planet due to the rotation of Earth. So the Coriolis Effect, along with the distribution of continents, gravity, and also friction, causes these things called gyres to form. So gyres are large circular loops of moving water. And you can see two gyres displayed here. Here's one gyre in the northern Atlantic, and here's another gyre in the southern Atlantic. So because these ocean currents are constrained by the two continents, and because of the Coriolis effect, which deflects or curves things to the right in the northern hemisphere or to the left in the southern hemisphere. Because of that curvature, you get a rotating loop of water. So these are known as gyres. And if you are struggling with the Coriolis effect, go and revisit the last lecture because we'll keep coming back to that again today. So each gyre, each subtropical gyre, is centered at about 30 degrees north or 30 degrees south. And you can think about them as being similar to squares in that each gyre has 4 sides. Right? So it's a circular shape, but a gyre has 4 different sides. So each gyre will have an equatorial current, will have a western boundary current, a northern or southern boundary current, and an eastern boundary current. Now here is a map of the gyres in a little more detail. So you can see we have the North Atlantic gyre here, rotating currents to the right or clockwise. And we have the North Pacific gyre here, rotating currents to the right. And then in the southern hemisphere, we have the South Pacific gyre rotating the opposite way to the left and counterclockwise. And we also have the South Atlantic and the Indian Ocean gyre. So those are the 5 main gyres, and make sure you know all of those 5 for your next exam. But you can see there are a couple minor ones here, right? You have a little mini gyre formed by the Alaskan current, the Norwegian current. So these are the major ones that transport the most water here. This next picture is similar to the last slide, but now I want to highlight some things that you couldn't see with the last slide. Here we have the North Equatorial Current and the South Equatorial Current. We can see that those 2 currents are both moving from east to west. So they're pushing water from east to west. And if we look at our wind belts, our wind directions, we can see that we have the northeast trade winds blowing from east to west in the northern hemisphere. And we have the southeast trade winds also blowing from east to west in the southern hemisphere. So we would expect surface currents to mainly parallel that, right? So that would make sense that ocean currents move from east to west. So here we can see that shown by these 2 arrows. But now let's look at some of the smaller little variations. Right? So here we have something called the Equatorial Counter-Current. And notice it's moving the opposite direction. Right? It's not as strong. Right? You can see by the length of the arrow that it's much less strong than the other 2.